Hello? Hello, can you hear me?
Yes.
Excellent. Okay. As always, it's having trouble starting, but it looks like it's working now. Okay. Let's see, it looks like we're all here. Okay, so this is the last of the regular sessions. And so what I want to do today is I want to keep talking about general techniques. And so the idea is to look at math that's related to Zeckendorf decompositions to get a little bit more sense of what we can do with this material. And leave a little bit of time to schedule when we will start our one-on-one meetings and to make sure that people understand what are the possible projects for the group research. So we've talked about looking at gap distributions. And I think there's a lot of exciting things to do for the simple and the compound path sequences because no one's really looked at stuff like this before. So there's a whole new feature. And that new feature is trying to deal with gaps that are now pairs rather than just integers. And that introduces a lot of technicalities and a lot of challenges. And when you're doing math, it's nice to have new issues that arise because when you solve them, then people take. Okay, so I'll skip a little bit of the problems. Now, we discussed differentiating identities last time, correct?
Yes.
Yes, so I'm not going to really talk about those. I'm going to just jump ahead. Okay. And so what I want to do is I want to talk a little bit more about estimation. So it's probably not going to be necessary in the calculations that you're doing, but these are very good techniques to know. There's a fun project I'm doing with one of my college students in probability where the solution uses techniques very similar to what I'm about to show you. And when we did the computer simulations, we got an almost perfect agreement with the theoretical prediction of 1 over square root of e. And when you get a number like 1 over square root of e, that means you're doing something right if it matches the numerics. This is not a number you find by mistake. So in case you choose to go a different route for the Zeckendorf projects, Stirling's formula will be useful, so let's just talk about it briefly. It's a way to estimate how large n factorial is. So it says n factorial is about n to the n e to the minus n. And what do I mean by about? Well, it's at least e times that, and at most e times n times that. Now you might say if n is huge, like 10 to the 50, differing by a factor of n is tremendous. But you've got to look at it as most of the term is that n to the n e to the minus n, especially if you take logarithms. So on a log scale, the amount we're off by is very, very small. And the correct answer is actually about halfway between e and en on a log scale. It's about square root of n, actually about square root of 2 pi n. As you see Stirling's formula on the bottom, so n factorial is about n to the n e to the minus n, square root of 2 pi n. And then it's an expansion. It's 1 plus 12 over n. And you can see that the terms are getting smaller and smaller with n. All right. So there's a lot of things you can do. I'm not going to really talk too much. I'm just going to have that slide there so you can always hit pause and go back if you want. So let's look a little bit at where things like this come from. There's a lot of ways to get to Stirling's formula depending on what math you know. So has everybody seen Taylor series or have you not seen Taylor series?
I haven't.
I have.
I have not.
Okay, so that's 2 no's and a yes. How many people have seen integration?
I have.
Okay, that's 1 yes.
I haven't.
I haven't.
Okay, 1 yes and 2 no's. All right, so since it's 1 yes and 2 no's, I'm going to just do this really fast. So if you haven't seen Taylor series and if you haven't seen calculus, I don't want to spend too much time on this. I'm just going to go very quickly. This will give you a little bit of a sense of some of the stuff you can do when you finally get to a calculus class. So the Taylor series of the log of 1 plus x is x minus x squared over 2 plus x cubed over 3, and so on and so on and so on. It converges if x is less than 1. whenever you have a product, you should always be thinking of logarithms because the log of a product is the sum of the logs. So the log of p is the log of n factorial. That's the sum of the logs up to n. And then the idea is we can approximate this with an integral. So the sum of log k is about the integral of log t. And so there are techniques, if you've done calculus, the idea of upper and lower Riemann sums, you can approximate things. This is essentially the integral test, and we can get a really good approximation for what's going on. And so we need the antiderivative of log t, that's t log t minus t. And when you go through and you put all the bounds in, after exponentiating at the end, when the algebra settles, you get very close to the right answer. And with more work, you can do even better. All right, I'm not going to go into too much of this again. You can just hit pause. But what's nice about this is by doing your more detailed analysis, you can get really good estimates for formulas like this. So if you haven't seen calculus, if you haven't seen Taylor series, you should take from this the motivation that the techniques that you'll be learning in a year or two are useful for solving problems, and that a lot of this stuff can be done, but the algebra can start to become intense. It can take a while to find what is the right path through the algebra to get a nice answer. All right, so what I want to do now is I want to shift to an interesting application of the Fibonacci numbers. And this is a game that I've created and had some of my students analyze. I have some current college students who are looking at generalizing it right now. And what I like about this game is it allows me to talk about some really good mathematics. And one of the whole purposes of our conversations is to show you a little bit of what's out there. So the idea is to discuss right now what's called summoned minimality. So we're going to write the Fibonacci numbers as f0 equals 0, f1 equals 1, fn plus 1 equals fn plus 2 is fn plus 1 plus fn. Now, if we write the Fibonacci numbers like this, we do have a slight issue. And the theorem below is not quite right. So how do I have to modify the Fibonacci's if I want Zeckendorf's theorem to hold that every positive integer can be written uniquely as a sum of one or more non-consecutive Fibonacci's?
You need to eliminate f0 because we need to keep the uniqueness, right?
Okay, so is it enough to eliminate f0?
And we also need to add the value of f2.
What do you mean by add the value of f2?
Because we want that recurrence to happen, and if we want to get rid of the value of f0, we must have f2 so that we can calculate the sequence, the following.
Well, if we eliminate f0, we still have f1 equals 1, f2 equals 1. So the sequence would just be 1, 1, 2, 3.
But we want like 1, 2, 3, 5, and 8, and so on and so on.
Right. We want to have the initial conditions being f1 equals 1 and f2 equals 2.
Yeah.
We don't want to have two 1s. Because
No, we don't.
we clearly can't have uniqueness.
Yeah.
So for example, 2018, last year would be the following. And we've talked about this. We've seen how you can use the greedy algorithm to find this. You throw away the largest Fibonacci number you can. You look at what remains, et cetera, et cetera. So if I have the expansion for 2018, how would you get the expansion for 2019? Would that be easy to find or hard to find?
Well, you can get rid of that 2, and then you adding a 3 so that we get 2019.
Yeah, we just add 1 to both sides, and then f2 plus f1 is f3. f3 and f5 are not adjacent, so we're fine. And we don't have to do anything more. But it's actually pretty easy if you have an expansion to get the next number, you just add 1. Now, Here is an alternate way, I think we've talked about this, to define the Fibonacci numbers. The Fibonacci numbers are the unique sequence of integers such that every number can be written uniquely as a sum of non-adjacent terms. So we start off with 1. We want every number to be represented as a sum of non-adjacent terms uniquely, so we have to add 2. We can't do 1 plus 2, so we add 3. Can we get the number 4?
Yes. 1 plus 3.
Good, so we can get 4, so we don't need to add 4, but we can't get 5, so we have to add 5. Can we get 6?
Yes, 1 and 5.
Can we get 7?
Yes, 2 and 5.
Can we get 8?
No.
No. So as a nice exercise, prove that this gives you the Fibonacci numbers. So frequently in mathematics, you have many different definitions for the same thing, and different definitions highlight different properties. This is an equivalent definition of the Fibonacci's. And you can just continue on and on and on. All right, now, let's look at a number like 18. If I use the greedy algorithm, I can write it as 13 plus 5. That's a legal decomposition, 2 summons. I could also have an illegal decomposition, 13 plus 3 plus 2, which has 3 summons. And a beautiful theorem is that there is never going to be a decomposition that has fewer summons than the Zeckendorf decomposition. You can't do better. So the example above shows you that sometimes the Zeckendorf decomposition will be better than other decompositions. Other times they might be the same. So can you give me a number that has 2 different decompositions and they both have the same number of summons and one of them is the Zeckendorf? So I want a number where there's another decomposition that has as few summons as the Zeckendorf. So is it possible that the Zeckendorf decomposition of this number would have just 1 summoned?
Yes, when the number is in the Fibonacci sequence.
Okay, but then you would need a way to write it as 1 summoned another way. Because we want to have a number that has a decomposition that has the same number of summons as the Zeckendorf. So if you are a Fibonacci number, can you write it as a decomposition of just 1 term other than just that Fibonacci number?
No, you can't.
So, okay, so this is how you think about things mathematically. Let's look at cases. Is it possible to have just 1 summoned? No. All right, so what's the next thing we should try?
2.
2. So if the Zeckendorf summoned, if the Zeckendorf decomposition has 2 summons, it's got to be, say, FA plus FB, 2 different Fibonacci numbers. So the question is, when can you write 2 Fibonacci numbers as a sum of 2 other Fibonacci numbers? So any thoughts on what you might try? Do you think the Fibonacci numbers would have to be close to each other or far apart?
What do you mean by close to each other or far apart? I mean,
Do you think the indices differ by maybe like 1 or 2 or 3, that the indices are very close to each other, or do you think they could differ by like 100 or 200? So you had F5 plus F100, okay?
Mhm.
You want to write that as the sum of two other Fibonacci numbers. But those numbers are very well separated. Do you think you can write F5 plus F100 as the sum of two Fibonacci numbers other than that way?
No.
No.
Okay, so why no? Because if you take F100, F100 plus F5 is basically F100. The F5 doesn't change things by that much. If you go from F100 to F101, it's way too large. If you go to F99, even F99 plus F98 is too small. So it's probably not going to be represented as a sum of two distinct Fibonacci numbers. So what else could we try for two summons? So remember, it doesn't have to be a Zeckendorf decomposition now. We want to find another decomposition that has the same number of terms as the Zeckendorf.
We probably need to try like a number that is a sum of 3 Fibonacci numbers.
Well, right now, I'm trying to think of just using two summons. We said that, you know, if we have two Fibonacci numbers and they're well separated, it looks like it's not going to work. So maybe they're not well separated.
Yeah, maybe they're very close.
They're very close. Could they be next to each other?
No, they can't, because that's not legal decomposition.
It's okay if it's not legal,
Oh,
right?
yeah.
But then that would reduce to just a one summon decomposition. So maybe try two Fibonacci numbers that differ by 2 in their index, or 3.
Mm.
And see if you can write that. So give me two Fibonacci numbers whose indices differ by, say, 2. So this is not a hard problem. Give me two Fibonacci numbers whose indices differ by 2.
Like F5 and F3.
Okay, so what's F5?
So F5 is 5 and F3 is 2.
No, F3.
F5 is A, right?
Is 8.
F5
Yeah.
is 8. So you have 3 plus 8 is 11. Can I write 11 as a sum of two Fibonacci numbers other than 8 plus 3?
No.
No.
No. All right, so now let's try having indices differing by 3. So instead of having F3 and F5, let's do F3 and F6. What's F3 plus F6?
16.
16. Can you write 16 as the sum of two Fibonacci's?
No, you can't. No, you can't.
Try again. It doesn't have to be a legal decomposition.
Okay, then 2, 8.
Yeah. And so that shows you that the Zeckendorf decomposition can sometimes tie other decompositions. If you have 2 8s, that's the same as a 3 and a 13. So again, the reason I wanted to talk about this was just the thought process of how you find something. You know, the first example showed you that the Zeckendorf sometimes wins. It's sometimes fewer summons. The next thing was to see if it's possible that there could be another decomposition that has the same number of summons as Zeckendorf? And the answer is yes. And you would first say, well, could it be just one summon? No, if it's just one summon, there's going to be a problem. Okay, what if there's two summons? Well, if the summons are very far apart, it's not going to work. So they've got to be somewhat close. They can't be next to each other, so let's try differing by 2, try differing by 3. And the idea is this methodical way of attacking problems. And as you go through this again and again and again, can you have a procedure that will help you find an example? All right, so you could also ask, what are the recurrence relations of sum and minimal? I'm not going to really talk too much about that. I'll have the slides here in case you're really interested. The main thing is we were able to come up with a nice condition on recurrence relations when they were sum and minimal. And so let me just give you a proof of why the Fibonacci's are sum and minimal. And this allows me to introduce some really nice math concepts. So let's say we have a decomposition. All right, so we have B1 copies of F1 all the way up to Bn copies of Fn. So this is not necessarily a legal decomposition. We want to show that no matter what decomposition we have, it cannot have fewer summons than Fibonacci, Zeckendorf. Okay? And what we're going to do is you give me a decomposition, I'm going to define something called the index. And this is very similar to a geometry class where you have to draw the auxiliary line. The hardest part of proofs is figuring out where to draw the lines. Here, it's what quantity do you want to look at? And so we're going to look at the index. It's going to be B1 times 1 plus B2 times 2 plus B3 times 3, all the way up to Bn times n. So which
why is Fn n? Because we know clearly that Fn is not equal to n. So,
I never said Fn was n.
sorry?
I never said Fn was n. Where does it say Fn equals n?
Okay.
I'm defining a new quantity, the index. So the number d, to compute d properly, you are absolutely correct that I can't use n for Fn.
Okay.
So for the index, which numbers count more towards the index? A number like F10 or a number like F1?
Could you repeat your question again? Then?
Sure. When you're calculating the index, which contributes more? The number of copies of F1 or the number of copies of F100?
F100.
Yeah. So we weight the contribution by the index. So F1, those B1s are just multiplied by 1, whereas the number of copies of F100 we have are multiplied by 100. So we can define anything we want. The question is just, when do we have a good definition? When is it useful? And so now, let's say we move to a new decomposition. So if we want to move to a Zeckendorf decomposition, we want to get rid of anything that's doubled, and we want to get rid of anything that's next to something else. So if we have 2 of some number, say we have F8 plus F8. I'm sorry, let's say we have 8 plus 8. That's the same as 13 plus 3. So with a little bit of algebra, you can see that 2fk is fk plus 1 plus fk minus 2. And so we've seen that in the case of 8 plus 8. This holds more generally. We have to be a little bit careful at the very beginning. So for us, we would write 2f2 is f3 plus f1. According to the formula, we should really be writing it as f3 plus f0. Well, for us, the f0 is going to be the other 1 that we're ignoring, that we should really have 2 1s to start the Fibonacci. So this is a rule to replace any index which is doubled. The next one is a little bit easier. There's no special cases. If we have two adjacent indices, fk and fk plus 1, then we can replace them with fk plus 2. Well, I guess there's a little bit of a special case. f1 plus f1 we will view as f2. So these are the legal moves that we can do, and we can apply these to any decomposition and start moving it towards the Zeckendorf. And now I can introduce one of the greatest concepts in all of mathematics, the monovariant. If you've done any math competitions, you might have seen this. It's a quantity that can only move in one direction. And the claim is that if I apply either of those two moves, the index of d prime is less than or equal to the index of d. So if you think about the contribution of, we say we have two fk's, and we replace that with an fk plus 1 plus an fk minus 2. When I do this, are you able to see my mouse moving back and forth, the little hand? Does that show up?
Yes.
Okay. So the contribution from 2fk, well, the index is just going to be the number of multiples times the index. So this will contribute 2k. This is going to contribute 1 times k plus 1 plus 1 times k minus 2. So it's going to contribute 2k minus 1. So we see that the contribution from 2fk is strictly greater than the contribution of fk plus 1 plus fk minus 2. And similarly, if we have fk and fk plus 1 and we replace them with fk plus 2, the left-hand side, the contribution to the index is going to be 2k plus 1, and the right side is going to be k plus 2. K has to be at least 1. So if k is 1, we get 3 versus 3. If k is 2, we get 5 versus 4. So once we hit 2, the left-hand side is going to be a larger contribution than the right. So what's nice is every time we do one of these moves, the index either stays the same or gets smaller. Any questions on this?
No.
Now what's nice is the monovariant can't move too much. Because if my number is less than the 50th Fibonacci number, I can't use any numbers greater than F50 in its decomposition. And so because of that, the possible values for the monovariant are bounded. And so if we're not at the Zeckendorf decomposition, we can keep playing these moves. And we'll get something that's either the same size or smaller. If you find this stuff interesting, a better quantity to define is a slightly different index. We'll call it index prime, where you take the square root of the number as the weight, not just the index. And so if you play with this, and again, this is a little bit hard, but it will show you that you can keep moving until you hit the Zeckendorf decomposition. If you're not at the Zeckendorf, you keep doing this, you have to show that it will eventually terminate. But there's only finitely many possibilities. With a little bit of work, you can do this. And it will prove that the Zeckendorf is minimal. So we don't really need this, so I don't want to go into too much detail. But I just want you to see some of the powers of stuff like this. And if you're interested, just email me and I'll send you the paper that has the full details. Okay, so I want to talk now about the Zeckendorf game. A lot of today's conversation, as you notice, is about how do you generate good problems? How do you attack things? How do you think about things? How did we find a number that had a decomposition with as many summons as the Zeckendorf? So you want to find methodical ways to attack things. But in addition to attacking things, you want to find good questions to ask. And so this is a game that I created to play with my kids. I have some students who are currently trying to generalize it right now. So it's a two-player game, and whoever goes last wins. So for a lot of these games, you have to be very careful. Is it who goes first who wins? Is it who goes last who wins? Or is it who goes last who loses? Frequently, it's trivial if you do it one way. So that's going to be how you choose which one. We'll see more about that in a moment. So 2 players, you alternate, player 1, player 2, whoever goes last wins. So here's how we play. The bins are the Fibonacci numbers, F1, F2, F3. And you choose a positive integer n, and you start off with n ones in bin F1, and all the other bins are empty. So if n is 10, we would have 10 chips in bin 1. And then on your move, on your turn, you can do one of 2 things. If you have 2 pieces in FK, you can take those pieces off and replace it with 1 piece at FK plus 1 and 1 piece at FK minus 2. And then similarly, if we had 2 F1, we would replace that with 1 F2. And the other thing we can do is if we have pieces at bins FK and FK plus 1, we can take 1 piece from each and remove those and put 1 bin at FK plus 2. Notice that these are exactly the stuff we were doing when we were analyzing the Zeckendorf decomposition and minimality a moment ago. So what we're trying to do is we're trying to play a game where we keep moving to the Zeckendorf decomposition. And the game is going to be whoever hits the Zeckendorf decomposition wins, because once you're at the Zeckendorf decomposition, is it possible that you could do either of these moves again? So imagine you're at the Zeckendorf decomposition. Can you do either of these moves?
Well, you can do the second move. If pieces at FK and FK plus 1 remove and add 1 at...
But we're at the Zeckendorf decomposition now. We're assuming we've played long enough so that we've hit the Zeckendorf decomposition. Will you have 2 adjacent pieces if you're at the Zeckendorf decomposition?
No.
No. So we can't do the second move. What about the first move? Could we do that at the Zeckendorf decomposition?
Yes.
So if you're in the Zeckendorf decomposition...
Wait. No. Because your FK are consecutive.
So we can't do either one of these moves if we're at the Zeckendorf decomposition. So it's clear if we hit the Zeckendorf decomposition, the game is over. It's not quite clear that we will always hit the Zeckendorf decomposition. That has to be proven. Okay, so here's a couple of questions you could ask. Does the game end? If so, how long does it take on average? How long does it take worst possible case? For each n, who has the winning strategy? Would you rather be player 1 or player 2? And then the last one is, what is the winning strategy? Now what's amazing is we will be able to prove that except for the case when n equals 2, and the game is boring then, player 2 always has the winning strategy. But it will be a non-constructive proof. And we'll talk more about that in a little bit. So let's play a game. So I talked earlier about having 10 pieces on the 1. Let's do that again. So we have 10 pieces on the 1. And we have 0 everywhere else. So what I'm claiming is, for the first move, player 1 has no choice. The only thing they can do is they can take 2 pieces on the 1 and replace it with 1 piece on the 2. Is everybody comfortable with this as the opening move?
Yes.
Yes.
So we would now go to 8, 1, 0, 0, 0. And if you look, 8 times 1 plus 1 times 2 is still going to add up to 10. Now I'm saying for my next move, player 2 is going to choose to take 2 things from F1 and make something else on F2. Could player 2 have done something else? So player 2 chose to combine 2 things from bin 1 and get something on bin 2. Could they have done something else? Did they have another legal move? So let's go back and look at the legal moves. So what are my two legal moves? Somebody tell me what the first move is over here.
So it's basically removing two pieces on FK and add one at FK plus one and FK minus two.
Okay, so that's the move that player two chose to do. They chose to take two pieces in bin one and replace it. And because we have to be a little bit careful, it's slightly different if you do it at k equals 1. Somebody tell me what the second move, whoops, somebody tell me what the second move is over here. What is that move?
So it's adding one at FK plus two and removing one at FK and FK plus one. So you can remove one from F1 and remove another from FK plus one and add one at F3.
Okay, so over here now, player one chose to take two things from bin one and put something in bin two. What else could they have done?
They
Well,
can also remove one from F1 and remove one from F2 and add one to F3.
Good, so that was the only other move they could have done. So now, let's look at this situation. Now it's player one's turn, and I'm going to say they're going to choose to take two things at F2 and replace it with an F3 and an F1. What else could they have done? Did they have any other moves?
They can also remove one from F1, remove one from F2, and add one to F3.
Good, they could have done that. They could have taken two adjacent ones, F1 and F2. What else could they have done?
Removing two F1 and adding one at F2.
Excellent. So as you go deeper in the game, you have more possibilities for a while. So over here now, there's only one possible move. They have to take two F1s and replace it with an F2. And now again, we have a lot of possibilities. So in this one, I'm saying they're going to take an F2 and an F3 and make an F4. What else could they have done?
They can remove one from F1 and F2 and add another at F3.
Yeah, instead of doing F2 plus F3, they could have done F1 plus F2. What else could they have done?
They can also remove 2 from F1 and add 1 at F2.
Excellent. So they keep playing the game. And now for this one, there's only one possible move. Take two F1s and make an F2. They could take two F1s and make another F2, or an F1 and an F2 and make an F3. They chose to take two F1s. Then they have F1 plus F2 is F3. They could have chosen to split the F2. They chose to do it this way. Now they can either take F2 plus F3 and make an F5, or F3 plus F5, or F3 plus F4 and make an F5. They chose to do an F3 plus F4 as F5. And now there's no moves left and player one wins. And so here's a summary of all the moves. And we can see player one wins. So I told you player two has a winning strategy as long as n is not 2. So obviously player two made a mistake somewhere. Does anything look strange about this table to you? Anything looks strange about this table? Would you normally see a table displayed like this? Something should be drawing your attention. Yes? I couldn't hear you. Could you speak up again? Something should look strange in this table. Normally tables are not presented like this. What is your attention called to when you see this table? So somebody needs to make a conjecture. Somebody needs to find something about this table that looks strange and speak up. So, given that nobody has spoken up yet, don't be afraid of saying something even if it turns out to be wrong. You know, look at this table. What looks strange to you about how it's displayed?
The maximum number after F2 is 2, right? Sorry, the maximum number after F1 is 2. Like, we only have 0, 1, 2.
Okay. That's a nice observation. We could have piled more things up on 2 if we had played the game differently. That's definitely something to notice. But just physically look at the table. Something should be strange looking at the table.
The arrangement of 0 is kind of strange. It is forming like a triangle up there, like as it.
Well,
Oh, they should probably like write a timeline to show like what is happening, because
all right, so this is time 0, time 1, time 2, time 3, time 4, time 5, time 6, time 7, times 8, times 9. What was strange in that? Don't look at the values, just look at how the table is written. Something should be strange.
Does it look like binary somehow? Oh, I think this looks like binary, right? If we look this from right to left.
But it's not going to be binary. And again, if we had a different game, we could have had more. We even have some numbers too. So it can't be binary. It's another good thing to try. But let's count again. Times 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What was strange?
there is some like blank space between two lines?
Yes, so please tell me you noticed the blank space earlier, guys.
Okay.
If you didn't notice the blank space, this is scary. This is staring right at you. This is the problem with algebra. You need to be able to look at things the right way. You should quickly be able to look at this table and see that the table is broken, that there's a blank line with nothing. Why is there a blank line with nothing? Well, over here, what did we choose to do? We chose to combine a 1 and a 2 and get a 3. Is there another move we could have done?
Well, you take away 2 in F2 and then distribute 1 to F0. Oh, to F1 and F3.
Yeah, we could split the 2 over here. And if we split that, we would take these two 2's, we get an extra F1 and an F3. And now in this blue line, there's only one thing we can do. Take 2 1s and make a 2. So the whole point of putting in the blank line is at that point, player 2 made a mistake. If player 2 had done this, it would have taken 1 extra move, and they would have won. So this is called basically a parity shift. Is there are key moments in the game when player 2 will have a choice, and they can basically force the game to get to a certain configuration. And they can force the game to get there in either an even number of moves or an odd number of moves. And depending on what they choose, that can help them figure out if they're going to win or lose. So the first theorem is that all games end in finitely many moves. I'm not going to go through the proofs. If you want, you're welcome to read the paper. It's not directly related to what we're doing, but a lot of it is still worth talking about as just good math and how to think about problems. There's upper bounds. There's things about fastest games. You can actually plot random games, and you can see it looks a lot like a Gaussian. And now I want to get to the key part, the most exciting part. Unless n equals 2, player 2 has a winning strategy. And the idea is very similar to that special game we looked at. That if player 1 has a winning strategy, then player 2 could steal it somehow. Unfortunately, the strategy is non-constructive. So right now, the US is getting ready for a presidential election in 2020. We have, I believe, 20 candidates on the Democratic side seeking the nomination for president. Imagine you are a political consultant, and you are hired by one of the candidates, and you tell them, great news, I've done the analysis, and you have a strategy which will win you the Democratic primaries, get you the nomination, and win you the general election. The candidate would be excited. They'd say, terrific, that's wonderful. What's the strategy? And then you will mark, well, it's a non-constructive proof. I just proved that the strategy exists. I don't actually know what you should do. Is that going to be useful?
No.
No.
Mostly no. At least the candidate would say, well, okay, if at least the strategy exists, then maybe I won't bow out of the race. Maybe I'll stay in the race. But just knowing that it exists is not that useful. Now, if you've done calculus, there's a lot of times where we know that something exists, like the intermediate value theorem or the mean value theorem. I know most of you haven't seen calculus. And we don't need to know exactly where it is to be useful. But here, unfortunately, it's a non-constructive proof. I'm going to give you an example of non-constructive proofs and non-constructive strategies with a simple game called Chomp. And the way it works is the following. You have a rectangle where you have at least 2 rows and at least 2 columns. Whoever goes last loses. So unlike the Fibonacci game, if you go last, you lose. And what happens is you choose a point. So I choose this point over here. And then you eat everything above and to the right. So you would eat these 8 dots. And then the next person would choose from what remains, and you eat everything above and to the right from that dot. Why do you think it should be whoever goes last loses and not whoever goes last wins? So imagine whoever goes first, whoever goes last wins. Where would player one go on their first turn?
Wally, what?
So imagine whoever goes last wins the game. Where could player one go on their first turn if whoever goes last wins?
Then you can just color the dot on the left bottom corner.
Yeah, if whoever goes last wins, player one would just choose this dot and win the game on one turn. Is this an exciting game?
No.
No. If player one can always win on the first move before player two does anything, this is not a game worth studying. It's boring. So this is why for this game, it's got to be whoever goes last loses. So I'm going to prove to you now that player two will always lose, that player one always has a winning strategy. And it goes as follows. There are two cases. So you have a configuration of the board. Somebody has to win. This game cannot end in a draw. So there's two cases. Either player one has a winning strategy for this board, or player two has the winning strategy for this board. Let's assume it's player one who has the winning strategy. Well, all they have to do is play that winning strategy. So in case one, when player one has a winning strategy, they just play it. So now let's look at case two. Player two has the winning strategy. So imagine player one goes in the upper right corner. Because we're assuming player two has a winning strategy, there is some dot which, if they color that, they will be on the path to victory. Let's say it's this one. And from this point onward, player two has the winning strategy. So what that means is whoever goes next on a board that looks like this loses. Player one originally went here in the upper right corner. Where should player one have gone? So we're assuming for this board that player two had the winning strategy. So player one goes here in the red dot, and then player two goes somewhere, say over here, and player two now has the winning strategy with this configuration. So whoever goes next from here will lose if the other person plays well. So instead of going in the upper right corner, where should player one have gone on their first move?
The place where the blue one, like, color its dot.
Excellent. Player one should have just gone down here. Because if player one goes down here, now player two is moving next. So what happens is it allows player one to shift places with player two. So they did this, temporary move. They saw what player two would have done. And then they actually says, well, actually, I don't want to go here after all. I want to go where you went. So the reason this is not constructive is we don't know who has the winning strategy. Remember, case one was if player one has the winning strategy, play it. And if case 2, if player 2 has the winning strategy, there's a way for player 1 to kind of sniff it out, but we don't know if that case happens. So something very similar happens for the Fibonacci game. So for the Fibonacci game, I'm writing the beginning of a board as follows. So the superscript tells me how many copies of that number I have. So this would be, I have n-3 ones and 1 3. I would have n-6 ones and 2 3s. Okay? And we start off at the beginning with n ones. So we're going to assume player 1 has a winning strategy. We're going to get a contradiction. So I will color things pink if player 1 has a winning strategy from that configuration, and blue if player 2 does. I'm going to prove to you in a non-constructive way that player 2 has the winning strategy if n is at least 3. And it goes as follows. Let's assume player 1 has the winning strategy. So I color the first box pink. How many moves does player 2 have?
1.
1. It's very nice when there's only one possible move. So because there's only one possible move, player 2 has to go here, and we have to color that pink. Now, how many moves does player 1 have?
2.
2. So it's possible that one of them leads to a winning path, one of them leads to a losing path. Let's think about it.
Oh.
I'm sorry?
Why are we coloring them both pink?
We really should only color one of them at a time,
Okay.
and you just do one case first, and then go back and do the second case. So we're going to really focus on the one on the left. And so over here, since this is a winning strategy, so player 2 went, player 1 goes here, player 2 goes here. So now player 1 can come to these 3 squares. So I'll highlight them as, so these are possible moves for player 1. And now, player 2 could move us to here. So let's go, look. So it starts off player 1, player 2, player 1, player 2, player 1, player 2. So at this point, player 2 has just gone, and it's n-5 ones and 1 5. Over here, player 1 has just gone, and it's n-5 ones and a 5. So these two boards are the same configuration. The only difference is who's going next. And so if this was a winning strategy for player 1 from this point over here, this would be a winning strategy from player 2. So what we could do is over here, we can start forcing things. So I don't want to go into all the details. I want to give you enough sense so that you can see what's going on. Is there a way to then say, well, if player 2 is over here, they can force the win, and then you can just move things upwards. All right. There's a lot of generalizations you can ask for something like this. And so I've got students who are looking at things related to this this summer. I want to shift back a little bit and just talk briefly about the projects you guys are going to do, and then try to set up individual times. So the first thing is to figure out what gap distribution we want to look at. So we talked about how there's 3 natural possibilities. You could look at, if you have 2 different summons, the summons are now going to be pairs of numbers. So when you subtract, you're going to get a pair with 2 elements. One possibility is to just leave it like that and say, how many times do we have a gap that's 1 0? How many times do we have a gap that's 0 1? How many times do we have a gap that's 1 1, 2 1, et cetera, et cetera, et cetera? The next thing you could do is you could say, well, what about having a gap where the sum of the elements is equal to a fixed number? So maybe if I want the sum to be 4, I could be 4 0, 3 1, 2 2, 1 3, or 0 4. And the last one is I could say, well, maybe I want to use something like the Pythagorean distance. You know, the square root of the sum of the squares, Or maybe just make things nice, just the sum of the squares. So if I have a gap of 5, or let's say I had a gap of 25, I would want two numbers whose squares sum to 25. So it'd be either 3, 4, 4, 3, 5, 0, or 0, 5. So those are the three most natural gap distances, gap metrics I can think of. There might be others. I think the easiest is going to be when you just look at it as a pair and ask, how often do you have 1, 0? How often do you have 0, 1? And if you go back and look at the paper and the argument in the slides when we did the gaps of the Fibonacci numbers, I think a lot of that will follow through. With a little bit more work, I think we might be able to get the gap where we define it to be the sum of the two components has a fixed value. So if the fixed value is 4, it's the 4, 0, the 3, 1, the 2, 2, the 1, 3, the 0, 4. The Pythagorean one where we do the sum of the squares, I think that's going to be harder. I'm not convinced we can get a clean formula for that. But no one has looked at gaps of summons in these decompositions. And so I think there's a lot that can be done here. I think those are going to be good problems to look at. All right, so is everybody clear on what to start looking at?
Yes.
Yes.
And you're all encouraged to talk to each other. Yeah, I would say we should really concentrate on the first two. But what's nice is we have 3 people. You can talk amongst yourselves. I also have several undergraduate TAs who are happy to chat and help us. Okay, so now it's time to try to find times for meetings. So let me pull up my calendar. Okay, so today is the 29th. So let's see. 29th of June. So I've got so June 30th, I've got a meeting. June 1st, I've got a meeting. July 1st, I've got a meeting. Is anybody free July 2nd? Can anybody do this time on July 2nd? 12:30 to 1:30 July 2nd. So nobody can do July 2nd at this time?
I think I can do. So
Okay. All right, so I will give you July 2nd. So we'll do 12:30 to, do you want to do 12:30 or do you want to do 12?
it doesn't matter. So you can just schedule the time.
Let's do 12:30. I'll block off 12:30 a.m. to 1:30 a.m. So email me that you are going to be taking July 2nd, which is a Tuesday. So can you send me an email?
All right.
Excellent. And then I'll send you a reminder before that. Okay. What about July 3rd? Can somebody take this time slot on July 3rd?
I think I have time.
Okay. So same deal. Send me an email. We'll do 12:30 to 1:30 a.m. So send me an email saying that this is going to be Wednesday, July 3rd.
Okay, sure.
And for stuff like this, it's always good to include both the day and the date of the week, because then if those two don't match up, you know that there's a mistake.
Okay.
Often I've seen people accidentally mix things up. All right, so we've got one person left. Is that correct?
I think 3 left. We have 3 left.
We have 3 left?
Yes. Me, David, and Heather, I think.
Let's see. Okay, so right now on the Skype call, I'm sorry, I've got 2 people left. Not
What?
3. So speak up right now if you have not been assigned a time.
I have
I
not.
haven't.
I have not.
I haven't.
Okay, so I'm seeing 6 people on the Zoom call. There's myself, there's somebody from the Eureka program is 2. So there's only 4 students on the call right now, and we've just assigned times to 2 of you. So this
No,
should-
we actually have 5 students. I think you need to click on the blue and white.
Oh, is that the issue? Oh, okay, there it is. Okay, thank you. It was hiding one person. Okay, so we've got, thank you. Okay, so we've got 3 more people to assign. Okay, thank you. All right, so can somebody do July 3rd? We just do July 3rd?
Yes. Oh, I can do July 3rd.
I think I am doing.
I think I already gave July 3rd to somebody, right?
Yeah, you gave July 3rd to me.
Right. Okay, and I've given. So let me just double check. Okay, how about July 4th?
I can do July 4th.
So let's do the same time, 12:30 to 1:30 a.m. Eastern. So send me an email and say that it's going to be July 4th, which will be a Thursday.
Okay.
All right, so now we have 2 people left.
Yes.
What about July 5th?
I can do July 5th.
Okay, so again, send me an email.
Okay.
And then what about, we've got 1 person left. Does July 6th work?
No, I actually have some time conflict with that. So I think can we do July 8th or 9th?
Let's do July 8th,
Okay, sure.
12:30 to 1:30 a.m. And July 9th, that will be a Tuesday.
Okay.
So wait a minute. Wait a minute. Oh, wait, no, July 9th is actually not good for me. Can you
Okay.
do July 8th?
Yes, July 8th works.
Okay. So let's do July 8th, which is a Monday.
Okay.
So let's check and make sure I've got. Let's see. So we've got. One. Just making sure we got everybody covered. Okay, so we've got times on July 2nd, 3rd, 4th, 5th. So I think everybody is covered.
Oh, and also, what's your email account?
Are you getting the emails from me? Because I said it right before the meeting.
I don't think so.
All right, so my email is sjm1 at williams.edu.
Got it.
So you must not be getting the emails I've been sending out. So if you email me, I will remind me when you email that you are not getting the emails, and I will try to fix that.
Okay.
All right, I will now work on posting the videos. Everybody have a great day. I'm looking forward to starting the research. Take care, all.
Take care.
Yeah.